Good morning, everybody, and welcome to the last chapter of this bunch, which is thermodynamics, okay? So the first exam is going to focus on this 4 chapters and only 4 chapters. However, the exam is not next week. The exam is toward the end of the month. So next week, we're actually going to introduce the second part of this class, which is relativity. I mean, it's amazing, actually, how we can cover relativity in 1 week. It's really something that is kind of fun to do, but we will try to do it anyway. Same thing actually with this chapter itself, chapter 20. Chapter 20 deals with the entropy, okay? And you will see the context in terms of a historical, at least historically, how the idea came about, and how the entire science of thermodynamics was actually came to be, and now its influence. And I already mentioned that before. At least the second law of thermodynamics extends way beyond thermodynamics. It's actually its influence. It's almost everywhere in science, biology. I mean, not just physical science, physics, of course, and chemistry. Not a single equation, not a single chemical reaction can happen if the second law does not allow it, okay? At least spontaneously. So if you want to happen it to happen and without being spontaneous, you will need to add catalysts, and those catalysts are actually dictated by the second law step. And the physical processes are also dictated by the second law of thermodynamics. So it's really impossible for anything to happen on its own without the second law saying so. And even if it's not going to happen on its own, the second law basically will dictate which way it goes. It also has influence on other subjects, not even science. I mean, philosophy. The flow of time. Apparently, time itself is tied to the second law of thermodynamics. It seems like the reason why I can and you can remember yesterday, but you cannot remember no matter how much you try tomorrow, is because of the second law. And that's the direction of time. It points toward how the second law is going to behave. So a lot of these things are because of that, related to that. And if we were to talk about it on all of these details, it's going to take more than one lecture. So it's impossible to do it in one day. So, but I'm going to introduce it, especially since it's the first time probably that you guys have seen it. We're going to introduce it from a historical perspective to see basically how it came to be. And we are going to introduce the 2 versions of it. The original version that Mr. Clausius introduced in 1850, around 1850, actually, that's when the idea started to float in his head first, and then later on adopted by everybody else. And then the second form of it, where Mr. Boltzmann actually laid the foundation for it, okay? So this is basically how we're going to, the 2 forms we're going to introduce. There are other forms of it. There are 4 more other forms to it, and they are all related to one another, okay? So let me share the screen with you, and I'm going to get right away to the subject, okay? I know in the book they put it toward the end where they talk about Carnal and his cycle and the second law, basically, and then they introduce the concept that Mr. Boltzmann basically stipulated at the end. So we're going to go there, and you will see the wisdom behind it, because once you introduce the second law, once you introduce Carnal cycle, then the Otto cycle, which is used in your car, or the diesel cycle, which is used in the big engines, basically, can be compared to it, can be compared to the Carnal cycle, because most of the times the questions are always related to how good is this engine if you compare it to Cardinal, because Carnal cycle is going to be the standard, okay? The other thing also, and I just remembered it now, is on the discussion session, there is about 5-minute video where I demonstrate this engine. Let me grab it. This is the Stirling engine, which is actually another cycle that is actually in the exercises. This is also the same thing. This is Stirling engine. I have several of them, actually. I demonstrated 2 of them in there. And Stirling engine actually turned out to be the next best engine after Carnal, except neither of these two are practical. Okay, that's why we use the Otto cycle for cars or lightweight vehicles, basically, and the diesel engine for the heavy machinery. So let me share the screen with you guys. So I urge you strongly to see that demo and understand the idea behind it, that is actually a 4-stroke engine. And I will explain all of these things, okay? So let me share. Where is the share button? My notes. Let me review an idea that we talked about last time, and that is the cycle. So if I have a PV diagram, okay? And if I have a starting point, usually the starting point is a good point to start from the compression stage, okay? So this is my starting point. And I go somehow, and I look at it, I'm going with the clock. That's how the clock goes, okay? And then come back to it. So it doesn't matter where I end up, where I go, but the ending point is the starting point. And it is in this fashion, clockwise. If it is clockwise, the area that is here, which is simply this let me pick up colors in here so that to see exactly what I'm talking about. Let me pick up the red color, which is really this area. Under this curve, I'm going to call it curve 2, okay? Minus this area, which is under curve 1, okay? That is how calculus works. This has nothing to do with anybody, okay? Take this big area and subtract from it this smaller area, and it's an arbitrary shape anyway. And at the end, you're going to find the area in between. You're going to find this area. That is W. That is the work. Okay. Obviously, this work is negative because this integral from here to here is positive. It's true. We're going from small values to a higher values. Okay. If this is the least point in here. Okay. And so it's going to be a positive value. And this is going to be negative because I'm going from 2 to 1. It's correct. So this area will turn out to be positive. However, the work has a negative in it anyway. It's not the integral of PDV, the way we defined it. So this is your volume. This is your pressure. So it's negative, the work of PDV. Okay. So this is how the work is. And this is for a cycle, by the way. So it's a good idea to put a circle in that. Okay. So the work will turn out to be negative, albeit the area itself without this minus will be a positive value, okay? It doesn't matter at the end because we're gonna write the expression for the entire energy as being Q plus W, the way we defined it, okay? Where the minus, if it turns out the work is minus, is actually lost in the form of work. Energy lost in the form of work, because this is the energy change. Okay. For a cycle, and I'm only talking about cycles, we're not talking about specific processes right now. Delta U is always 0 because my starting point is my ending point. So that means Q net is equal to minus W net. And W net is this area. So this is what I meant by W net. There will be at some points in the cycle where heat is entering the system and the heat is leaving the system. But what I'm talking about is the net heat. How much heat is overall, coming in and going out, the difference between them, the algebraic difference. So this is basically for a cycle that is described in this fashion, okay? Since the W is negative, that means energy is lost in the form of work. This is an engine doing work, okay? This is an engine doing work. That's basically what this thing is. It is losing energy in the form of work, losing, or how do I say it? Energy lost in the form of W. That's basically what that means, okay? Now, I mentioned Q net. W net is clear. W net is just this area. Q net in general can be written as Q that is taken into the system minus Q that is lost to the system. But since I'm adopting this option, excuse me, this sign convention, I'm going to call this one the heat that is added to the system. And I'm going to call this one the heat that is lost to the system. H for hot, heating it up, and C for cooling it down. When it's cooled down, that means it's lost. So this is actually a negative number. This is going to be a positive number because it's heating it up. It's increasing its temperature. Okay. So this is basically what this algebra is looking like this. So here is how diagrammatically this looks like. I have somehow a place where I'm extracting heat from it. I'm dumping heat somewhere else, and I'm doing work in here. Remember, the work is just the difference between the two algebraic values, or the sum of the two algebraic values. One of them is positive, the other one is negative. So in other words, I can say W in absolute value is equal to Q hot in absolute value, that is the heat that is added, minus Q that is actually left the system and cooled it down. So that's basically what the expression looked like. This is because delta U is 0, because it's a cycle. Okay. So in here, I'm going to define the efficiency as being E equal, by definition, the desirable over the cost. This is what it costs you really to do that work, is that heat that is added to the system. I mean, this is actually a side effect. Okay. QC is a side effect. So we don't enter it in here. Okay. What we want from an engine is work. What it costs us is that heat that is added to it, because that's ultimately where the work is coming from. Because delta U at the end stays the same. So somebody has to pay for this. And that only person is the hot source. That's it. Okay. So this is in a nutshell how the efficiency is defined. The efficiency can never be greater than 1, always less than 1. At most should be 1. If QC is actually 0, if QC is 0, if there is no heat lost at all, then in this case, QC is 0. So the ratio will be exactly 1. Okay. However, we will assume that this is not possible. E can never be equal to 1. E is always less than 1. That is basically what the second law says. That's exactly what this whole point is in here. Oops, what this popped up in here for? Okay. So this is the engine. Let's describe a similar process and try to define another similar quantity, but in the other direction. So again, I'm going to stay in here, but I'm going to go this way first and come back this way. So note my direction now is counterclockwise. So again, this is the PV diagram. So this is counterclockwise. Okay, so this is against the clock. The clock goes this way, and now we're going in the opposite direction. Everything is going to be reversed now. Everything is going to be done in different fashion. First of all, W will be positive. This integral, the upper one, to find this area, is going opposite from lower to higher. So it's going to be a negative value. So this is a negative value, and this is positive. So this is positive. So when you subtract a smaller number that is positive from a negative number that is bigger, the answer is going to be negative. So this area is going to be negative, but don't forget the minus. Remember, W is always still minus the integral of PDV. So what I was talking about earlier is just the integral of PDV over this cycle. So it's going to turn out to be a negative value times a negative, so W is going to be positive. So in this work, in this thing in here, I need to add work to the, I need to add energy in the form of work. So energy added in the form of work. This is called a heat pump. This is not an engine. It's not producing work for you anymore. It's taking work to do what it needs to do. So in this case, it's a heat pump, which breaks down into two kinds of applications. Either cooling device, like an AC, like a refrigerator, and so on and so forth, okay? Or a heating device, like what we have in the winter, heaters, okay? So the desirable thing in here is still either QC in the first case or QH in the second case. It's the same device, actually. All you have to do is reverse it, that's all, okay? It's the same device. On one side, it's going to give you QC, and on the other side, it's going to give you QH. It's not going to give you QC, actually. It's taking heat from the system, making it cooler and cooler. So it's taking it and dumping it to QH and making it hotter and hotter. So if you want cooler, put the side that is taking the heat to you, and then it's going to take heat from you. It's going to make it cooler for you. If you reverse the same device and put it in the opposite direction, now it's going to take the cool from outside and bring it to you, and I mean dump the, making the outside cooler and making the inside hotter. So it's the same device that works this way. So it's going to dump QH on one side and extract QC from the other side. And in doing so, you have to supply your W to it. W is supplied now. It's not extracted anymore. So if you want hot, you have to stay in here in front of it, because it's going to extract the heat from the environment and put it to this side. If you want it to be cooler in the summer, you have to be on this side because it's extracting heat from where you are. So it's the same device. It's a heat pump. Now, the efficient, again, delta U is still 0. Okay, and it is always true that W net is equal to a Q hot net minus QC net. QC, there is no net in here. That is Q net. Okay. Okay, this is true all the time. The thing with it is, it's kind of where you want to be. That's all. Okay, what do you want to do with these devices? Now I'm going to define cup, COP, the coefficient of performance. Again, what you want, the desirable, over the cost. The cost is going to be W now. That's what you have to pay for. Your AC unit does work, and you have to plug it to the wall, and that wall extracts energy from the wall and need to do work to pump that air, to pump that heat, okay? That is what you need to pay for. Except now the desirable could be QC for an AC unit or QH for a heating unit, that's all. So there are two kinds, either QC over W for a cooling, like an AC unit, and QH over W for a heater. Okay, in typical situations, and let me explain the second part, okay? Let me explain the heater first. The heater, according to this expression, what is it? What did I write it? Here, the heater QH is going to be W plus QC, that's all. So for the heater, is going to be QC plus W over W. From this expression, from the conservation of energy, from delta U. QH is QC plus W. So this expression is going to be 1 plus the other one, QC over W. So it really is one more than the other, that's all. Always one more. That's because of the conservation of energy. Okay. So when I ask for the coefficient of performance, typically what we ask for is this value. Because once we know this value, it's easy to find. So this is your, for the cooler, okay? For the AC unit, if you wish, okay? For the refrigerator. So when we ask for QC over W, we are actually immediately finding what the other one is. So they are related. I mean, because of conservation of energy, they're different only by coefficient of 1. Number 1. Number 2, this number is always greater than 1. QC over W is usually more than 1. So unlike the other way around, where we found it to be always less than 1 for the engine, this one is always more than 1. Okay, and why would I say usually? Because there are exceptions. We might be the heat pump maybe not working properly, and it's losing a lot of heat, and it brings the number down. Okay, let's take an example. Okay, for an AC unit, or at least the standard. The standard. Let's go back into this definition here: QC over W, and W, remember, is QH minus QC. And QC is proportional to the temperature, and we're going to see that. And QH is going to be proportional to the temperature, and we're going to see that. For a unit that works between 0 degrees Celsius and 35 degrees Celsius, which is extremely cold and extremely hot. These are extreme cases, okay? For something that works in between, its coefficient of performance is going to be even higher, okay? So this is a typical value. So in this case, if I define the QO, doesn't matter which value I'm going to find, it's going to be for the AC unit, it's going to be the QC is at 0 degrees Celsius, and 0 degrees Celsius is 273 Kelvin, divided by the difference between, that is where W is, the W is between QC and QH, and that is 35 degrees Celsius, the difference between them. In other words, 273 plus 35 and 273, the difference is going to be 35 Kelvin no matter what. This number is big. Let me check quickly how much it is. I'm just giving you this because in some questions in the exams or tests or things like that, you might encounter something like this one. So I don't want to see a value for the coefficient of performance that is less than 1, okay? So when you calculate it, it should be typically more than 1 because of this fact. So let me do 273 divided by 35. Oh no, I need the numerical value. It's giving me 39 over 5. 7.8. Which means for a heater, it's going to be 8.8. Okay, it's more than 1, more than 100%. That's the point I'm trying to make in here. So if you are calculating the efficiency, and if you know the system is going through this type of work, okay, if it is an engine, you determine that it is an engine, and you were set to find its efficiency is less than 100%, no matter what. And the second law will ensure that. If it is a heat pump, okay, and I made this path look a little bit easy. This path could very well be this path, okay? Now we're talking hypothetical, okay? This path could be like this. So I really have to find this area and find it if it's positive or negative. If it turns out to be positive, then I'm dealing with a heat pump. If this area turned out to be negative, then I'm dealing with a heat engine, okay? All of this are academic examples, and we're going to get the practical examples very soon, okay? So the point being in here is if this area turned out to be positive, then I have to find the coefficients of performance, and the coefficients of performance better be greater than 1. If the area turned out to be negative value, then in this, that means the work is negative. That means you really are getting work out of this thing, which is an engine. Then I have to find the coefficients of efficiency of that one, or the efficiency, E. Some books, they use the letter eta, I think. That's for the same thing, okay? Some of the references, they use that letter for the efficiency. And in that case, it has to be less than 100. Less than 100%, I should, less than 1, okay? 0.7, 0.9, it doesn't matter. Okay, so this is cycles. There are 2 types, counterclockwise and clockwise. The net of which you can end up with a positive work or a negative work. A positive work is for a heat pump. That means you have to supply your energy in the form of work. And a negative work, that means you're losing energy in the form of work. That means you're getting work out of it. That's an engine, okay? So this is, in a nutshell, what this whole thing is all about. Around 1824, an engineer in the French army working on the railroad by the name of Sadi Carnal. I know in English probably is not said like this, but that's how his name is. He was working in the railroad and he asked a simple question. What is the most efficient engine? Remember, he's an engineer. He's not a physicist or a chemist or biologist or any other scientist. He's an engineer, okay? This is the only science that I know of that was started by an engineer. So it's a science that was, if you wish, built up by an engineer, okay? Not a scientist of some sort, okay? So he asked, what is the most efficient engine? Remember, at that time, you have a boiler room, you have basically, you supply the wood or whatever thing is in there, and the water vapor evaporates, and that turns some turbines, and turbines gets the wheel going, and the engine gets going, and so on and so forth. Is it the one made out instead of steel? Probably we could made it out of aluminum. Maybe we could, instead of water, we use alcohol. Maybe we use different materials and things like that. Okay. In doing so, he came up with, tried very hard, and at the end, he came up with that engine. So he answered the question. Okay, from 1824 to 2022, that's almost 200 years. Not a single person could come up with a more efficient engine than Mr. Cardinal. And there are all kinds of companies out there. There is Toyota that claims the most efficient cars with Honda. Then you have Teslas, and you have all kinds of things. Although granted, those engines are working with different principles. They're using electricity, but it's still the most efficient engine is that of Cardinal. Isn't that amazing? So let's try to see. So he answered the question. He said the following: grant me the following thing. Grant me that heat cannot transfer on its own from a cold source to a hot source. I will show you the answer. I will tell you the most efficient engine. This statement, which is everyday experience, you take a cup of water that is cold from the refrigerator, heat will come from the environment to it, okay? Not the other way around. It's not going to happen so that the cup of water that was cold becomes colder. It's not gonna be, it's gonna get hotter. So why is it gonna get hotter? Because getting heat from the outside to it, which was hotter to it than it. If you take a cup of coffee that is extremely hot and you put it on the table, okay? 10 minutes later, half an hour later, an hour later, you're not gonna get it even hotter than what it was before. It's gonna be cooler. Why? Because it's losing heat to the environment. So this is basically the idea behind it. So this sounds intuitive. This sounds normal because that's everyday experience, okay? He said, if this statement is true, I will show you the most efficient engine. Okay, so that's basically what it is. This is the second law of thermodynamics. It was not recognized as so when he said it. It was in 1850 when Mr. Clausius, Rudolf Clausius in Germany, started thinking about that same problem, and he introduced the energy conservation in the form that we use today. So this is in around 1850. Delta U is equal to Q plus W, and we still use the same symbols that he used then. Then this became the first law, and this was, he dubbed it actually the second law. Mr. Clausius put it together. You see how the second law came first, about 26 years earlier than the first law of thermodynamics? Because at that time, the idea of energy started to take hold in physics and other subjects, chemistry, and so on and so forth. So he introduced this when there was a lot of criticism for Mr. Clausius for this thing, and they accused him of cheating and doing all kinds of things, that these ideas are not his, but he borrowed them and he's claiming things. But he's the one who actually laid the foundation for the entire science. He was a great teacher, but he's the one who put all of these things. So almost 26 years later, when the first law of thermodynamics was postulated by Mr. Clausius, after the second law was discovered first. Then, as I mentioned before when we introduced the whole subject, the zeroth law was introduced because there was a need to understand what this temperature business is. So we introduced the zeroth law later on, okay, to make this thing make sense. All of the first and the second law make sense. See how this whole science was discovered first by an engineer, backward, okay, starting from the last law, at least in the bunch that I mentioned so far, being first, and the second law being first, and the first law being second, and the last law, which is the zeroth law, became last. So it's kind of a backward stuff in here, okay? But this is really what the statement is. So this is not the only form. This is the original form. I'm going to have two more forms, okay? And that is part of the discussion item. You need to list all of these three different forms, okay? At least that I'm going to talk about. Two of them, we're going to talk about them today, probably. And the third form is going to be discussed this coming Thursday, okay? So there will be three different versions of the second law of thermodynamics. They're all identical. So this is the original form as put in here. So here is the story. I have a TH, This is a heat sink, meaning no matter how much heat you dump in it, it's not going to change its temperature, like the ocean, okay? If you take a cup of water and you put it in the ocean that is super cold, frozen, is that going to warm cool the ocean? No, the ocean is too big to begin with. So this is a heat sink, meaning no matter how much hot stuff you put in it or cold stuff or how much heat you take from it, its temperature stays the same. It's the same thing, for example. That's because the cup of water that is supposed to be too cold, when you put it in the ocean, it's supposed to extract heat from the ocean. So not going to cool it down. The temperature stays the same for the ocean. So this is what we mean by heat sink. Like the air, for example, I was giving examples earlier in the room. Its temperature is not going to be impacted by a cup of water that is super cold or a cup of coffee that is super hot. It doesn't matter. So the air in the room is not going to change because that is considered a heat sink. So the temperature is fixed. That's what a heat sink is. There is another one sitting at T cold. That is another heat sink, okay? That absorbs heat at will, and its temperature is not going to rise from TC. And this one, it's a heat sink that is also going to lose heat at will and its temperature will not change, okay? This is what the second law is saying. This process is a no-no. On its own, spontaneously, without, I mean, you're telling me, how about the heat pump that we were talking about? Isn't it exactly what we were doing? Isn't it exactly what the heat pump is doing? It's taking QC from one side and dumping it into all the already, this is room, which is cold room, and the outside that is hot. You're taking heat from here. No, this is the other way around. The outside in the winter is cold, and the inside is usually warmer, okay? So this is hotter. But you're still taking heat from the cold and you're dumping it. I mean, the outside temperature is usually lower than the inside temperature in winter, okay? And that's what the heater does, okay? So you're taking heat from the cold and you're dumping it in the hot. So you're telling me, how come this does not violate the second law of thermodynamics? It doesn't, because you have this guy. This is not spontaneous. This is not on its own. You need to have an external thing that does that for you. So a heat pump is not in violation of this second law because there is actually work supplied added in here. So that is not what we're talking. We're talking spontaneously, like a hot cup of coffee, for example, and the environment. Then in this case, heat will flow on its own fine. So this is in agreement with the second law. Okay, this is what we're talking about. Let me describe the cycle that Mr. Cardinal has proposed, and we're going to find its efficiency, and we're going to take it from there. So this is the cycle that he proposed between these two temperatures and these two temperatures only. So you have the PV diagram, pressure and volume. You have your TC, I mean T hot, I'm drawing it in here. So this is your T hot, and you have your T cold. He says, so this is an isothermal, and this is an adiabatic. And this is another isothermal, a TC. Isothermal. Did I say thermal? E. And this is another adiabatic. Okay. So this is Carnal cycle, provided you do it extremely slow in a fashion that is reversible. Meaning from every point, so we're going through an engine, okay? So we're going through clockwise, okay? We can say this is my starting point. This is A. VA I meant. This is VB. This is VC. And this is VD. Obviously, the pressure in here is PA. The pressure in here is PB. The pressure in here is PC. And the pressure in here is PD. In other words, this point is A, this point is B, this point is C, and this point is D. Okay? Two isothermal. One is an expansion stage. Okay? One is a compression stage. Where the volume shrinks. Two adiabatic processes. One is an expansion, and one is a compression. Okay? Because these are adiabats, there is no heat involved. However, there is heat getting into the system at this stage, Q from the hot source. Okay? There is Q that is dumped to the environment at this stage. In other words, QC is negative. Because the work is positive. That means we're adding work during this stage. We're compressing the gas. We're adding more energy in the form of work. Let me explain why that is. We're going from VA to VB. So the integral itself, in this case, PDV, is negative because the final volume, namely VB, is less than VA. So this value itself is negative. Times a negative becomes positive. So this is the work in the stage between A and B, going this way. Okay, so that work is positive. And it's an isothermal. That means delta U is 0. So that means Q from A to B, which I called QC quickly, must be equal to the negative of this negative, which is the positive of this volume VA from VB of PDV. And this is negative. This whole thing is negative. The integral itself is negative because you're going from the higher value down to the lower value. And this is basic calculus. This value better be negative. In other words, this area itself is a negative area. Typically, if you integrate from VB down to VA, that is going to be a positive value because it's above the x-axis. Okay, had the graph been below the x-axis, then you probably will end up with a negative area. But in this case, it's going to be a positive area. Granted, you go from VB to VA, but you reverse the polarity of this integral. You reverse the ends of this integral, meaning at the end, you're going to get a negative value. So that's why this heat QC is actually a negative value. Why? Because delta U is 0. It's an isothermal. Okay. For the same reasons or the opposite reasons, QH is positive. QH is clearly positive. QH, which is still the positive of the integral of the work, except it's going to be, the integration is going to be from VC to VD, and that is a normal integral of PDV. This integral is going to be positive. Why? Because we are integrating from the lower value to the upper value. So no matter how the shape is, it's going to be a positive value. QH is positive, QC is negative, and there is no Q in these cases because they are adiabatic processes. So that's all the Q's we have for this problem. These two values only. And the work is going to end up being a negative value. I'm running out of colors in here. The work is going to end up being a negative value because it's an engine. I mean, the process itself is clockwise. So the work at the end, the net work is going to be a negative value. This is the Q net. It's going to be QH plus QC. One of them is negative, the other one is positive. but one of them is greater than the other. QH is more than QC. It's above QC. The curve itself is above. So that's why the integral for this area is clearly bigger than this area. Okay, so at the end, Q is going to be a positive value. If I add it to W, add this 2, I better find 0. Why? Because I went through a cycle from A to B to C to D to A. So there is no change in the, this is W. I mean delta U, I'm sorry. So delta U, which is the sum of these 2 points. So delta W is going to be negative in this case, which means I really have an engine. It's doing work for me. Okay, so this is the way this process is described. We're going to do the calculations, but let me show that this is actually the most efficient engine. Why this is the most efficient engine? Okay. The key word is actually it's a reversible process. Let's think about it for a second. Imagine we have a Carnot engine. This is a hypothetical, okay? That takes 100 joules from TH, from the heat sink that is sitting at TH. So it takes 100 joules from here. And for some reason, it gives us 60 joules of work. So if we apply this principle, this is how this engine look like. This is TH, this is TC. It takes 100 joules from here, dumps the difference and gives us 60 joules. The difference is 40 joules. So this is your QC and this is your QH. The difference between them is the W. That is by conservation of energy because delta U is equal to 0 overall the entire cycle. Okay, so the entire cycle, we take 100 joules here, and we the exhaust system in this case dispenses of 40 joules, and the net work is going to be in this area, in this case, 60 joules. This is a hypothetical example. Proper calculations probably will give you different numbers, but I'm just giving you an example why this is going to be the most efficient engine. Let's say, for example, that somehow we have a better engine than this, okay? Where we actually, let's say, for example, we invented, we claim, this is claim. So this is our claim, that we have invented an engine from the same hot source that takes 100 joules. It's going to give us 80 joules of work. Obviously, it dispenses of only 20 joules in this case to the cold source. So this is our claim. This is what we are claiming to be true. Okay. Turns out we're going to be liars, and we will see why. Okay. So this is our claim. We're claiming that we have a more efficient. Obviously, the efficiency of this engine is clearly E. For this, it's going to be 60 divided by 100. It's going to be 60%. So that is the efficiency of the engine. Our efficiency, our claim, so this is Carnal, is going to be 80 divided by 100. It's going to be 80%. Okay, that's why I chose this round number, so much easier to do the calculations in here. So this is our claim. We'll see that this is not going to be true. Okay, let's see why. Imagine with me, I chose bad numbers in here, okay? Can I change this engine to be only 40 joules? Lower its. So Carnot engine is 40%, okay? I mean, I even made the claim even more, how should I put it? More pointed, more basically, we're making a big claim in here, not a small claim that we're improving the performance by only 20%. We're improving it by 100%, basically from 40%. Up to 80%. That's easier for me to do the analysis. Otherwise, I'll have to do the common denominator and all of that nonsense, which I'm not really ready to do at this point. Hopefully, you guys understand that this is a hypothetical example, so I can choose the numbers whichever I am, as long as I'm claiming that this is a Carnot engine. So the Carnot engine in here is 40%, and my claim can be anything as long as it's more than Carnot engine. And I'm going to show that this cannot be true. This is impossible by the second law of thermodynamics. Let me see why that is. If Carnot engine can give you 40 joules this way, all I have to do, because it's a reversible, remember, we were very careful to do this process so that it's a reversible. What that means is PV equal to nRT at any given point. It's in thermal equilibrium at every given stage, okay? That is what thermal equilibrium is. Real engines, they fluctuate every time you go from place to place, and they are actually a mess. So real engines are not, they don't really observe this law until you wait a long time for it to settle down at a given point in here. So these things in here we're describing are ideal situations, and that's why it's going to turn out to be more efficient than anything. So let's take Carnot engine again for a second and double it. So if I double Carnot engine, the hypothetical Carnot engine, so from the same heat source, so basically double the machinery, whatever you have. If you had 2 wheels, make it 4. If you had a 1 belt, make it 2 belts, and so on and so forth. So make it twice as big as it was. So in other words, you're not going to take 100 joules from the hot source. You're going to take 200 joules from it. So you're going to take 200 joules from it, just to match your 80 joules in here, okay? And then, since you're going to get 40 joules from a single engine, you're going to get 80 joules from this engine, okay? And at the end, you're not going to dump 60 joules, you're going to dump actually 120 joules to the environment. The efficiency is still the same. The efficiency is still 80 over 200, which is still 40%. All you did was double Carnot engine. If you have one engine, put 2 next to one another. So instead of taking 100 joules, you're going to take this much, 200. And instead of dumping 60 joules, you're going to dump 120. And instead of producing 40 joules, you're going to produce 80 joules out of it. So you doubled Carnot engine. And now, since it's a reversible, all you have to do is reverse the whole process. Instead of going this way, go counterclockwise and make it into a heating pump instead. Now, reverse the new engine, reverse it. So this is how it's going to look like now, since it's going to be a reverse process. It's going to have the TH. It's going to dump the 200 joules. It's going to require an 80 joules to do its job and extract 120 joules from the source. So it's going to work as a heat pump now. And that's fine. There's no problem with it. It's a reversible to begin with. There's no problem with it. So this is how the engine is going to be reversed and to become a heat pump instead of an engine. Now, take the engine that we made the claim for. So this is our claim now. Take this one and connect it to this one. So this is how it's going to look like. From the other one, you're taking 100 joules from the hot source. You're getting 80 joules in terms of form of work. And you're dumping only 20 joules to the TC. If you connect the two together. So now they become one unit. This 80 joules that is produced by our claim is going to be immediately put into Carnot heat pump. And then all of a sudden, from outside looking in, it's only one device, basically. Okay, it's only one device that looks like this. Because this 80 joules is canceling each other. So it looks like we have TC, we have TH, where we are taking 100 joules, but we're dumping 200 joules at the end. So we're dumping 100 joules, the net. Where are we getting this from? We're getting it by dumping 20 joules to the cold source, but extracting 120 instead. So the net is we're taking 100 joules because 120 minus 20 is actually 100. So this looks like a process that is not helped whatsoever. There is no external machinery to this entire device to help it extract 100 joules from the cold source to the put it in the external source, which is really a no-no. This is a spontaneous process now. Why? Because this machinery now is internal. So whatever it is, it's doing its own and working without help from outside. No external input. So this is spontaneous process. And this violates the second law. Okay, this is in violation of the second law. So there is something wrong with our argument. Either Carnot engine is not feasible, and it is a theoretical engine and it's perfectly legitimate, or our claim is outrageous. And that is the answer. So our claim is false. So this is not true. We cannot do a better engine than this one. The reason why is because Carnot engine, first of all, uses only two heat sources, two temperatures basically, only. And there is no heat in between them other than this during those two temperatures. And it's reversible. So this is really the most efficient engine you can claim. So if somebody goes and does a bunch of engines and claims that one of them turned out to be more efficient than Carnot engine, you know that that person either is a liar, or that person has actually made mistakes, one of the two, okay? Is everybody so far so good with me? Following the argument that I just followed? Yeah. Okay, very good. Okay, so let me.
I have a question.
Yes.
Why is it those specific numbers?
No, this is just hypothetical numbers, just to here is the case. Okay, that's a good question. Let me go back into the diagram. Okay. So the actual engine for a Carnot engine, and we'll see the efficiency quickly, okay? We're going to find what that efficiency is. It has to do with the two ends of the temperatures. So I took just some specific numbers for me in here so that the math works. If I stuck with the 60 joules in here and the 80 joules in here, I would really have to work out a certain number, including fractions of these numbers, of the Carnot engine to match that 60 joules. Okay, with the 80 joules. And then I will have to find the least common multiple of the two numbers and have fractions of this one and multiples of the other, or multiples of the other and fractions of the other. So I come up with a 3 of one and 4 of the other. And then at the end, the numbers will match for me. So I rechange the numbers so that only 2 would work with 1, because 2 times 40 is exactly 8. That's why I ended up with only 2 of them. Okay, so this is just an example, okay? This is just an example to improve the following, that if you do, even with the least common multiple of the two engines, and reversing Carnal cycle and making it into a heat pump, or the outcome, basically, how many of them you bring up, you're gonna end up with this scenario. In either case, you're gonna end up with some sort of mechanism that is enclosed in such a fashion with no external input. Heat will flow from the cold source to the hot source, and that is a no-no. That is the whole point. Does this make some sense to you, Maddie?
Yes.
Okay, very good. So basically, that is the whole point in here. So I just took out some simple numbers in here to make the case. So what is the efficiency of this engine now? Well, the efficiency is easy. So it's going to be, let me go back into the black pen. It's going to be E equals to W I'm going to put it in parentheses because I know it's going to be a positive number, okay, divided by QH, because it's an engine. The desirable thing is the work. The cost is that energy that you have to take from the hot source. In other words, there is a boiler room that you have to bring wood to it and boil the stuff in it, okay, make the water boil, okay. So that is the cost. That is what costs us. The exhaust that goes from the system and the air, the heat that escapes, that is actually a side effect. And I mean, that's the cost we have to pay also, but it's not like, that's not something we pay directly. As a matter of fact, we lost it, okay? So that is basically the bottom line. So let's find this efficiency. Obviously, W from this expression of the conservation of energy, it's simply equal to Q, the net Q, which is QH minus QC. E is equal to, if I want to write, remember QH is positive and QC is negative. So it's going to be QH minus QC over QH. And this can be written as 1 minus QC over QH in absolute value. That's it. Or if you wish, you can write it, and you have to be very careful in here. How should I write it in here? No, let's leave the minus sign intact, because QC is negative and QH is positive. You could write it that way. But granted, you know that QC is negative. No, QC is, what am I writing? It's plus. QC is negative and QH is positive. Okay, so to alleviate you of all of the headache, just put 1 minus the absolute value of the ratio of the two. Okay, it is important, this expression, for exams and homework. Sometimes that's all you're given, and that is the efficiency for anybody. Okay, at least this way it's anybody, any engine. Okay, and I think in one of the intro problems that you guys have in the pre-exam, pre-test, that was one of the questions. They give you an engine, they tell you how much work, and you're supposed to find how much heat was taken, and you're supposed to find the efficiency. Okay, so this is one of the things that you're supposed to know. Like, for example, I just did the math. If it's 40 joules that was done in the form of work, then in this case, the efficiency is clearly 40 over 100, which is 100%. Sometimes they give you, we take 100 joules from the hot source and we dump 60 joules. How much is the efficiency? The efficiency is going to be 100 minus 60, which is 40 divided by 100. Or they tell you, for example, we got 40 joules and we dumped 60 joules. How much is the efficiency? What is going to be 40 over 40 plus 60, which is the same thing. So that is how the efficiency is. And that is one of the things that you're supposed to know from this class, okay? So that's a good question for Maddie, okay? Again, since I mean, her question is actually a very good question because it really relates to that topic, which is one of the objectives of this class, to know how to find the efficiency if you know the work, or the heat, or the QC, okay? Or the total QNet. So that's one of the questions. But we're going to take a step a little further than that. So we're going to find the efficiency for the Carnot cycle C to be 1 minus the heat that is, remember, we did this calculation a long time ago. Q at an isothermal, any isothermal process is nRT, T is constant, ln of V final over V initial. I'm taking it in absolute value because depending, if I'm going from here to here, Q is positive and it's actually equal to the, in this case, this is V1 and this is V2, turn out to be nRT ln of V2 over V1, okay? And if I'm going in the opposite direction, Q is going to be just negative nRT ln of V1 over V2. And that's the properties of the natural log, okay? So it's going to be the final volume, except I have For the first one, I'm going from VC to VD, and that's for QH. And for QB, I'm going from VB to VA, okay? And the minus is there already taking care of those absolute values. So I better put the numerator correctly. So here is how this expression would look like. NRTC, because it's in the numerator, the Q has C in the numerator in this form. NRTC here for QC times the natural log of the final value, and the final value is VB over VA, or VA over VB, because I already took the sign out. So it's VA over VB divided by NRTH now for QH. And that is sitting at a temperature 2H. So it's going to be TH. ln, the final volume, is VD, and the initial volume is VC. So this is this isothermal. ln of VC over VD over VC. Okay, VD over VC. Okay, of course the NR cancels, and the efficiency will turn out to be E of Carnal 1 minus TC ln of VA over VB divided by TH times ln of VD over VC. That's the same expression as above. I'm going to show that these two ln's are the same ln, the same number. The ratio is 1. I'm going to show that very quickly, actually. Remember, going from D to A, that's an adiabatic process. Going from B to C, that's an adiabatic process. That means that from D to A, it's an adiabatic process, which means that the temperature at D, which is TH, by the way, times the volume at D to the power gamma minus 1 is equal to the temperature at A, which is T cold, times the volume at A, let's see, at A to the power gamma minus 1. So this is an adiabatic process. The same thing in going from B to C, that's also an adiabatic process. So that means the temperature at B, which is TC. Oh, this is TC, I'm sorry. Yeah, it's temperature, cold temperature. So, okay, so let's write it at TSC. Let's write it from B to C. At the point C, the temperature is hot, and the volume is VC to the power gamma minus 1 is equal to the value B, the temperature is cold, TC, times the volume at that point B to the power gamma minus 1. So this is the expression for the adiabatic processes. All I have to do is take the ratio of these two expressions and we're done. Divide this number by that number. TH cancels TH. That's why I wrote it on this side, by the way. And TC cancels the TC. Okay. And it would be left with VD over VC, which is the denominator, to the power gamma minus 1, and VA over VB, which is the numerator, in this case of the natural log, to the power gamma minus 1. So what this gives me is VD over VC to the power gamma minus 1 is equal to VA over VB to the power gamma minus 1. This is a VC, by the way. All I have to do is take the natural log. So it's gamma minus 1 times the natural log of VD over VC is equal to gamma minus 1 times the natural log of VA over VB. Obviously, it can cancel with respect to gamma minus 1. If somebody has a mathematical background in the class, they probably will lose sleep over this thing, Mathematicians always worry about what if the case gamma is equal to 1? What happened then? Okay, what is going to happen at that point? No, all of that. Gamma can never be equal to 1. Remember gamma, which is by definition Cp over Cv, when Cp is Cv plus R over Cv. So it's always going to be 1 plus something R over Cv. In other words, gamma minus 1 is going to be R over Cv. So physicists and engineers and scientists usually don't lose sleep over this one because they know exactly what the value of gamma minus 1 is, which is just a non-zero value. Okay, so constant over a constant, and it turns out to be a number. Okay, so we're going to cancel with it. So that is my point in here. ln of Vd over Vc is the same of ln of Va over Vb. So this term cancel using the adiabatic part of it. So at the end, the efficiency will simply be 1 minus Tc over T hot. So to go back to the example that we were talking about, that engine, for example, that is working, let's say, for example, between room temperature at 25 degrees Celsius. So this is your Tc. And let's say, for example, it's boiling at 100 degrees Celsius. So the efficiency, degrees Celsius, is going to be, and this is where you have to be extremely careful. These temperatures are measured in absolute temperature and Kelvin, not actually in. So this is going to be 1 minus Tc, which is 25 plus 273 divided by 373, which is 100 plus 273. Quick calculator in here. So 1 minus, of course, we're going to write it in percentage. So let me put the n first in front of this guy. Otherwise, it's not going to give me the 293, is it? I don't know. 98. 25 plus 273, how's that? Divided by 373 and close the parentheses and enter. It's giving me 20% efficiency. So that 40% was really a very, very high number for an engine, okay? Even for a Carnot engine. So 20% is just, I mean, no matter how good your the engine is, because of the second law, that's part of the depressing thing about the second law. The first law says that the energy is conserved, which means that you can break even. The second law is really saying that you cannot even break even. That's really part of the depressing part of the second law of thermodynamics. Even in that case, you cannot break even. And that is really how this thing is. So we still have about 10 minutes. Let me, so we found the efficiency. The efficiency for the Carnot engine is always given like this. So if you're asked in an exam or a test or a homework problem to compare the engine you're working with the Carnot engine, for the engine that the practical engine that you're working with is going to be E equals to the work divided by QH. And this number will always be less than this number. So if they tell you to compare this engine, the one that you're dealing with Carnot's engine, you have to find the highest temperature and quality H. You have to find the lowest temperature and quality C and apply this formula. Had that engine been really a Carnot engine, this is how much its efficiency is going to be. You will find that this number is always less than this number. Okay, there is probably an exception with a Stirling engine, but that's something else. Anyway, the point being in here is that this is the comparison. So this is, again, pointers to how you do your problems and how you solve equations and things like that. They will always sometimes ask you, hey, how is this engine compared to the Carnot engine? Had this engine really been a Carnot engine, how efficient it's going to be? You will find that this efficiency is less than that of Carnot engine. And how can you find that Carnot engine for that specific engine? You look at the highest temperature in the cycle, call it TH, and the lowest temperature, call it TC, and use this formula. And now all of a sudden you have what the efficiency would be had this thing was operating as a Carnot engine. Okay, so let me introduce what Clausius has introduced. When you look at this process, when you look at this equation, when you look at the entire Carnot cycle, QH is higher than QC in magnitude, but TH also is higher than TC. And he kept on looking at that relationship between the temperature and the heat, okay? And he noticed that, first of all, for this process, the ratio of QH over TH is the same as the ratio of QC over TC, at least in magnitude. Because the temperatures will cancel from the numerator over the denominator, and you will end up with the natural log, exactly the one that I was talking about. And at the end of the day, the ratio is going to be 1, because if you take the QC and you divide it by TC, you will end up with NR times the natural log of this ratio. If you take NR, TH, ln of VD over VC, that's QH, by the way, and you divide it by TH, the TH drops from this expression, and you will end up with an NR times the natural log of these two numbers. And the NRs cancel, and the natural log, I just argued that they do cancel too. So at the end, the ratio is 1, is the same. So there is a quantity that kept on popping up. There is no such a quantity in this part of the cycle because Q is 0. You take 0 and you divide it by any T in here, and there are a bunch of them from TH to TC, you're going to get 0 anyway. So a quantity that kept on popping up for him all the way through is Q over T. That's Mr. Clausius, by the way. Okay, that quantity, first of all, he looks at different processes. It's still continuing, and he kept on adding it for a cycle. He noted that if he added dq over T over an entire cycle, that thing will vanish for a reversible processes. For a reversible process, that thing always cancels. For a non-reversible process, it's always positive. This quantity can only be greater than or equal to 0. In other words, it takes from the hot source an amount, and it dumps an amount to the cold sources in the process. But at the end of the day, the negative part will always be less than, at most equal to, the positive part. So this quantity is always positive. Why? Because of the second law, the one that the other one postulated. So he gave it the letter S, and he defined it S in such a way that ds is equal to dq, okay, over T. I don't know if anybody knows why he chose the letter S, okay? And he gave it, the first one, the equivalent value or something like that. That's how he named it. Until later on in one of his papers, he chose the name entropy for it, which is coming from a Greek word that means energy or heat or something like that, okay? So that is how the word entropy was first introduced. So this is the entropy as defined for an infinitesimal process by Clausius himself. And the symbols are used till today as we did them. And the change in the entropy overall is given by, of course, the initial and the final, whatever that is, of how much heat was added or subtracted to the system per unit temperature. So that's how he defined it, okay? That's how the entropy is defined. It turns out for a reversible process, for an entire cycle, the value is going to be 0. In other words, if I take these two values, for a Carnal cycle, for example, delta S for a cycle, not any cycle, for a Carnal cycle, for the first part, what I mean by the first part is this QH. It's QH constant because the temperature is not changing in this whole thing. So I don't need to integrate anything over anything, because even if I want to integrate, at the end of the day, 1 over T becomes constant because the temperature is, so I'm dividing it into 4 sections. Okay, this is the first one. So 1 over TH, the integral from basically the initial point, which is, what is it in the diagram? We called it ABC. We call it C. From the point C to the point D, from CD, of dq, okay? because the temperature is constant throughout that thing. So you can take it out of the integral. Plus, the second part is going to be 0, because 0 over t going from d to a. And that is going to be 0. It's a bounded integral where you're integrating 0. There is no heat in here from d to a. And then from a to b, it's going to be, temperature is also constant, but it's Tc in this case, plus 1 over Tc, the integral from a to b of dq, or nothing over dq only, because I took the Tc as a common factor in here, plus the third process, or the fourth process from b to c, and that is going to be a 0 also for the same reasons as, so this is 0 because it's an adiabatic process. And this is 0 because it's an adiabatic process. And this is going to be turn out to be actually nRTH over TH times the ln of the V final, which is VD over VC. And this is going to be nRTC over TC times the ln of the V final, which is VA over VB. I'm sorry, over VB over VA. The final is VB. This is going to be a negative number. Cancel the TC, cancel the TCH. This is going to be a negative number and equal to that amount, so it's going to be 0. That's the point in here I'm trying to make. It's going to be 0 for this whole entire cycle for the same amount added in here and there, and one of them is positive, the other one is negative, so it's going to be 0 for Carnal cycle. We're exactly at the minute where we're supposed to stop. So let me summarize right now. What this law now says is, this is basically what this says is, the second law now can be postulated by Clausius as delta S can never be negative. Delta S can never be negative, can never be negative. The change in entropy can never be negative for a closed system. So this is the second closed system. This is the second way of saying the second law of thermodynamics. And this is in compliance with the fact that the system can, there is no spontaneous way for heat to transfer from a cold source to a hot source. They are the same exact statement. Either you say delta S can never be negative, or, so in other words, this is impossible. Only it's 0 for special case and special case only. It's always positive. Okay, I think we're a minute after the time. When we come back next time, we're going to finish this idea when we explore what the entropy means with the order and disorder. And then we are going to talk about the Otto cycle, which is a practical engine used in cars. And then we're going to talk about the diesel engine, which is used actually in heavy machinery. I already mentioned the Stirling engine, and we're going to get it in examples. We'll do some examples, and we'll talk about the lab. And the lab is extremely important for you guys in terms of exam. Okay, so it's really help you in terms of preparing for your exam. Any questions? No? Well, I'm going to stop.
I have one, just to clarify, it was ds is equal to dq divided by t, and EC is equal to 1 minus TC divided by TH for the formulas.
Can you point me exactly, because I lost some of the, I don't know exactly what are we talking about in here? ds is dq over dt. That's by definition of the entropy.
Definition of entropy. And then the EC one, you said that was another, you circled that one or squared it?
I calculated it for 4 processes of the entire cycle. 2 adiabats, and that's there is no heat exchange. So the entropy is, there is no change in the entropy. That's why they call the isentropic processes, because the entropy doesn't change for those 2 processes. And then I calculated it for the case of the isothermal process, the first one, And the isothermal process, the second one, it turns out to be the same value, except one of them is positive and one of them is negative. That's all. The logs are equal in magnitude, and we have shown that. And they are actually opposite in sign because the ratio is backward. That's all.
Oh, okay, okay. I thought they were. Yeah, never mind. Okay, that makes more.
We
Okay.
showed earlier that the logs are the same. Actually, when I went through this calculation, they're the same logs, except the ratios now are, I followed the boundaries of integration, and one of them is negative and the other one is positive. The NR is the same. So then two logs are the, so it's just to argue the case that the entropy for a Carnal cycle overall is going to be 0. And that is because it's an ideal cycle. It's a cycle where it's a reversible. So it's one of those cases where the entropy doesn't change. Typically, in any problem where you're asked, if you don't find it, I mean, if you find it negative, you have to redo the calculation. Okay.
Okay.
If you find
Fair
it
enough.
is negative, that is when you know that it's like, for example, somebody asks you to find the square root of a number, and that number turned out to be imaginary when you know that you're dealing with a realm of real numbers. Okay. Doesn't make sense. Okay. I'm going to stop the recording. And one of you guys need to stay with me because he asked a question. I don't know if he's still around or not. So I'm going to stop the recording. Where is the recording?